Good morning, everyone. I, on behalf of SAARC Energy Centre, would like to warmly welcome you all to today's webinar on opportunities and challenges in new markets for the offshore wind. My name is Tanjin Jamso. I have recently joined in the SAARC Energy Centre, Islamabad, Pakistan. And prior to joining this center, I have worked in the hydropower sector, mainly in Bhutan, uh, involved in the operation and maintenance of the hydropower plant, then the construction of the hydropower plant, and strategy formulation mainly for the hydropower plants. And SAARC Energy Center being a technical arm of SAARC, we are pursuing mostly with the member states on what the emerging technologies are concerned, and we are trying our best to share knowledge among the member states. In that way, so this today's webinar is being organized to share knowledge on the potential of harnessing offshore wind among the sub-member states. So with that, I would like to request Mr. Abdul Rashid Joheko, Director, SAARC Energy Center, Islamabad, to kindly deliver his open speech and open the webinar. Over to you, Director.
Thank you, Mr. Tandon. Dear participant, speaker of the webinar, good morning to everyone. My name is Abdul Rashid Jokyo. I am Director, SAARC Energy Center. It's my pleasure to welcome you all to this SAARC webinar on the opportunities and challenges in new markets for offshore wind. As you know, SAARC Energy Center, being a technical arm of the SAARC Secretariat, our center has taken numerous efforts to promote development of renewable energy, mainly from solar, wind across the South Asian region. Renewable energy has become cheaper than all fossil fuels, leading global investments in renewables to surpass these fossil fuels. In 2024, renewables overtook coal as the world's largest source of electricity generation. Further, is highlighted in COP30, emphasis has been made to triple renewable goal from 4.4 terawatt 2024 to 6.9 terawatt by 2030, in which harnessing of the renewable power from the offshore wind is included. Ladies and gentlemen, according to 2025 report of the World Wind Energy Association, global wind power capacity reached 1.117 terawatt by the end of 2024, supplying nearly 10% of the world's electricity demand. Offshore wind accounted for around 83 gigawatt of this capacity. Under ARENA's planned energy scenario, offshore wind capacity is expected to reach 275 gigawatt by 2030 and approximately 1,200 gigawatt by offshore wind energy offers a strategic opportunity for the South Asian countries. The SAARC region benefits from favorable wind regimes across the Arabian Sea, Bay of Bengal, and Indian Ocean, particularly near Bangladesh, India, Maldives, Pakistan, and Sri Lanka. Although large-scale offshore wind farms are not yet operational in South Asia, several pre-feasibility assessments and site identification studies have already been undertaken. Harnessing offshore wind power will support energy diversification, promote industrial growth through new job creation, and contribute to region's climate change commitments. This webinar aims to provide participants with insights into opportunities, challenges, and enabling conditions for the offshore wind development in South Asia. Dear participants, we are honored to have with us distinguished expert Dr. Guru Raj, Assistant Professor of Indian Institute of Technology, Kanpur, India. His insights, expertise will undoubtedly enrich our understanding of opportunities, challenges in today's webinar. I extend my sincere thanks to all the participants for joining us today. I encourage you all to make this an interactive, engaging session. Please feel free to share your thoughts and to contribute towards the discussion of the session. With these words, I declare the session open and wish you all the productive, enriching learning experience. Over to you, Mr. Tandon, for taking the session further. Thank you.
Thank you, Director, for your kind words, and especially for the benefits of the participants at large, and for highlighting the potentials we have in among the South members and the goals set by in COP30 to triple the harnessing of renewable energy. So that this will help us in uh, the technical persons and the persons involved in various countries to give insight of what we have to do for harnessing this wind power. So with this now, the session, I will be moderator for today's webinar. First, there will be a presentation by Dr. Gururaj. It will be around 30 to 40 minutes. Based after that, then question answers will be followed. So, Dr. Gururaj, so over to you. Please take us through your presentation.
Thank you so much. I'll just share my screen. Please confirm whether my screen is visible.
Yes. Yes, Dr. Gururaj, please go ahead.
Okay. So thank you so much for this opportunity again. So the topic that we have chosen for today's discussion is the opportunities and challenges in new market as for offshore wind energy. So just to introduce the topic, so what is the potential of wind energy, the installed capacity across the world? As you can see with the picture, it's steadily increasing. The growth is steadily increasing over time. The global wind power capacity as of now, the installed is 1,173.5 gigawatt, which is nearly 10% of total electricity demand. And among them, onshore capacity is 1,088 gigawatt and offshore is 83 gigawatt. So this is the installed capacity as of now. It is projected to increase by 2030 around by 275 gigawatt. And the offshore wind energy potential that we all can witness, hopefully if we live by then, 1,200 gigawatt by 2050. So it's a significant ambitious growth that is expected over a period of 2.5 decades. And let's all witness to be part of that glorious occasion. And then you can see in the specific to Asia Pacific region, the total wind energy capacity installed as of now is 785 gigawatt. Among them, the onshore wind capacity is 780 gigawatt and offshore is 5 gigawatt. So the South Asia in specific, the total wind energy capacity is 53 gigawatt. As of now, we don't have any offshore wind energy being harnessed, but it is expected to pick up in shortly. So with respect to the countries, you can see India has good scope. Pakistan, Maldives, Sri Lanka, Bangladesh. These are the potential regions where we can harness offshore wind energy. So comparative studies also put up. So onshore capacity installed of various countries in South Asia. India is 52.1 gigawatt, but we don't have any offshore as I've already mentioned. But it is expected by 2030 that an offshore auctions would take place and 37 gigawatt nearly. So Pakistan 1.84 gigawatt is the onshore, and Bangladesh is 62.9 megawatt. So like this, Sri Lanka 15 megawatt, Maldives 0.6 megawatt. So there's some scope for offshore as well in these countries. So what is the potential in the SAARC countries? So India has a potential of 70 to 74 gigawatt of offshore wind energy exploitation. Pakistan has also 50 gigawatt, Bangladesh 10 gigawatt, Sri Lanka 56 gigawatt. These are all very good numbers. So, but to reach to this potential, to really make it feasible, so there are certain challenges as compared to the onshore wind energy system. So let's go through these challenges and try to see, how we can address them. So the first challenge is, as we all can, by common sense, think of is harsh marine and weather conditions, right? So offshore sites face strong winds, high waves, storms, and corrosions, and weather restricts installation and maintenance windows, increasing delays and cost. And the second challenge is the high installation and infrastructure requirements as well. So we need a specific vessels, heavy lift cranes to mount the plant, and then deep water ports may also result in quite challenging installations, and foundations need to be very concrete and robust. So it requires precise geotechnical assessments, and then cable laying in deep or rough seabed conditions is technically demanding. And then with respect to the, let's say you have installed the wind turbine. Now ultimately the objective is to convert wind energy into electrical energy, right? So there are issues associated with the electrical energy transmission, and then eventually bringing the cables to the land as well. Certain challenges that I have listed here: long subsea cables introduce losses, require careful thermal design, and are prone to damage. Offshore substation must meet strict grid codes like fault right through, reactive power support, harmonics, these ancillary services. No matter we have a wind plants onshore or offshore, these challenges we are supposed to address them. But offshore becomes even more challenging as we have difficulties reaching out to the turbines in case of any cable damage or so and so. So that's what the protection, coordination, synchronization, and SCADA integration could be a complex game. And apart from this, we have high operation and maintenance difficulty because access to turbines is difficult due to sea states. We all know that sea states may keep changing. Sometimes it could be calm, sometimes it could be quite violent, and so it could be challenging for us to reach out there. Vessels or helicopters are often required. And then repairs and troubleshooting at sea are time consuming and expensive. Reliability issues like gearbox, power converters, blades have greater impact on the offshore plants. Apart from this, if you speak about the mechanical and structural fatigue, so there could be naturally there is continuous combined loading of wind plus waves, which leads to fatigue and stress upon these blades increases, and not only the blades, the towers and drivetrain, a lot of disturbances and turbulences being exposed on upon these parts. So we need a robust infrastructure to make it more stable. Larger turbines of up to 15 to 30 megawatt may face more complex challenges in terms of the resonance and dynamic performances. So apart from this, because we are going to disturb the life in the marine, so we need to also look into this aspect of bird migration, and how does we going to take care of the local issues like noise, and impact assessment on the environment also has to be carefully monitored. And then apart from this, there are hardly a few manufacturers who are specialists in manufacturing blades, towers, and subsea cables. So there could be challenge with respect to supply chain, and shortage of installations, vessels, and port infrastructures may also delay the overall installation. And the whole stuff requires a lot of capital investment. So cost overruns due to weather delays may also add on to the burden. So financing depends heavily on long-term stability of policies and power purchase agreements. So overall, so many dynamics, but yet the motivation is that it's a green energy. There are certain advantages also that we'll discuss as we move forward. So the technology gaps, like especially the floating offshore wind, we have floating platforms require advanced mooring systems and dynamic cable designs. Long-term reliability of floating system is still being validated. Integration with existing ports is complex due to platform size, and there are health and safety challenges also. Working at heights, offshore transfers, and harsh conditions increases safety risk. requires specialized training and emergency response planning as well. So you can see the trend of offshore turbine size. It is increasing as we progress in our technological advancements. Large turbine ratings comes up with the capacity of have grown from 5 to 8 megawatt to 14 to 18 megawatt, reducing cost per megawatt. And longer blades like 100 to 120 meters using carbon fiber composites reduce weight while increasing swept area, so leading to more feasibility of capturing the wind energy. So floating offshore wind technology enables deployment in deep waters where fixed bottom turbines are impossible. Dynamic cables and flexible mooring lines adapted to platform movement. And floating platforms allow access to high wind speed regions far from shore. So these are some of the latest technological advancements that is helping us to take this technology to the next level. Future offshore farms are evolving into multi-energy hubs, integrating offshore wind plus offshore solar. So that's quite interesting because the floating solar is also becoming popular. So why can't we put up this solar beds along with the wind turbines? So the main advantage that we all can figure out is, especially in the onshore plants, we have solar and wind hybrid plants across various places. So solar being available during the daytime and wind energy is quite active if you see the wind profile. So it really picks up well during the late evening hours and late night hours. So both of them combined together can bring up can really reduce the storage capacity required to make it more reliable plants. So both are complementary to each other, and there could be a lot of cost optimization in terms of space, storage, and in fact, in one of my PhD work also, I worked on bringing these two technologies together, and I've also noted that a lot of converters and Paltronics switches and then the filters can be optimally utilized so that we can reduce the overall cost of this technology. So hopefully we can look into these options as we move forward. So overall, this allows stable and high capacity energy export. So, and then advanced SCADA and cyber security. So high resolution data acquisition with sub-second sampling. So this is an advancement that is motivating us. So secure high bandwidth fiber links for offshore communications, real-time control for coordinated turbine form optimization. So you can see here we have offshore platforms, wind farms, and they are connected to the common control center, which is located onshore, and the substations and utility scale DRs, they're all communicating in real time to the control center, where we can think of the parameters that need to be observed, and if there is any proper control actions that can be initiated, especially this energy monitoring, and if in case if we can offer some of the if there is some stability challenges that can be sorted out, because offshore plants mostly we connect through HVDC, and HVDC is known for improving the stability of the overall system. So then offshore wind farms can become really handy supporting the system to improve the stability, both in terms of frequency stability, voltage stability, and if there is any fault, and then we can also think of fault rate through options as well. So making it more optimistic in terms of improving the overall resiliency of the system. And apart from that, the digitalization, automation, and smart operation and maintenance. So the predictive maintenance using artificial intelligence, machine learning, and digital twins reduces the downtime. In fact, we have also got a research funding project where we are working on artificial intelligence applications to predict the precise solar and wind forecasting, so that we can reduce the overall tariff, and economic dispatch could be also much smoother. So for prediction purpose and maintenance purpose, no doubt AI can really support us. and condition monitoring systems for blades, bearings, converters, and cables. So this is also an important area because we need to exactly predict when what is the durability of the blades and the turbine and other mechanical devices, so that we can plan well in advance before the system collapses. We can change certain parts, make it more reliable in due course of time. So autonomous drones for blade inspection and offshore survey, robotic crawlers for turbine blade inspection and underwater asset monitoring. So really, this is becoming more interdisciplinary, bringing computer science engineers, the automation engineers, the electrical engineers, mechanical engineers, civil engineers, all of them put together in one platform, working towards this technology is really overwhelming actually. So uh, so let's move on to the energy transmission and grid integration innovations. So offshore HVDC converters platform enable long distance power delivery with lower losses, as I've already mentioned. So HVDC in fact projects are really picking up well, especially the northeastern states of this of India. I've personally read through that there are a lot of installations of HVDC is going on, and multi-terminal offshore HVDC grids are being developed for future energy hubs, and high capacity subsea cables with improved insulation and thermal performance, advanced protection and control systems including wide area monitoring and fast fault ride through. So overall we can see there is technological advancement happening at the grid integration level, grid automation, and grid edge orchestration to make this system more smarter and more resilient. So cost reduction technologies, ultimately everything, the technology becomes only feasible and can sustain over a long run if it also can support the economical benefits. So standardized turbine components and mass manufacturing will certainly helpful for reducing the overall cost, and improved installation logics and optimized vessel scheduling, advanced project planning using 3D digital models and simulations. So will also support us in terms of cost reduction. And the total installation cost values decreases with time due to technological advancement. You can see how over the period of 10-20 years, the on both onshore and offshore plants. So the cost cost per kilowatt in terms of USD, it is projected is decreasing. So this is very welcoming. So, however, offshore wind turbines are more costly compared to onshore technologies for obvious reasons that we have already discussed. It's quite challenging, and we cannot compare in terms of cost truly. But naturally, there is inclination towards offshore also because the wind is freely available, and we need to explore that opportunity as well. So, what are the solutions for environmental and noise mitigations? So bubble curtain systems and vibro pilling reduce underwater noise during installations. Bird detection radars and AI-based wildlife monitoring systems reduce ecological impact, and low noise blades designs to minimize acoustic emissions. So these are some of the latest technologies that are adopted. So what is the market status of offshore wind energy? For the 7th consecutive year, China added the most offshore wind capacity of any country. With 4 gigawatt added to the grid in 2024, the country reached 41.8 gigawatt by the end of 2024. So you can see in the picture like how it is really picking up. So mostly it is dominated by China, around 50%. The global offshore wind market has been growing by 10% on average each year over the past decades, with total installation of 83.2 gigawatt, representing 7.3% of the total wind capacity by the end of 2024. And there's so many other countries also which are picking up gradually. With respect to Asia Pacific region, APAC contributes 55.6% of total installed capacity, and China is the absolute market leader. I've already discussed about that. South Asia region is not participating in the offshore installed capacity as of now. So global offshore market outlook by 2034, you can see 350 gigawatt of new offshore wind capacity to be added over the next decade, bringing total offshore wind capacity to 441 gigawatt. And the compound annual growth rate is expected to remain the highest until 2030. So CAGR represents compound annual growth rate. In total, 215 gigawatt of offshore wind capacity is predicted to be added in the next 10 years, of which 36% will be in 2025 to 2029, and the remainder in 2030 to 2034. So the top 5 markets in APEC for offshore wind additions over the next 10 years will be China, Taiwan, South Korea, Japan, and Philippines. Within the South Asia region, India is expected to contribute about 1.9% to offshore wind deployment. And other South Asian countries such as Pakistan, Bangladesh, and Sri Lanka do not have concrete offshore wind deployment plans as of now. So the capacity utilization factor, we have put up this table just to have a comparison between offshore, onshore, and solar PV. So offshore is best among the renewable energy resources. It is 40 to 60%. And onshore wind is 25 to 35% CUF. And solar PV is 15 to 25%. So resource quality, offshore is very strong and consistent wind, low turbulence. And onshore, we have moderate wind and higher turbulence. Solar PV is highly dependent on sunlight availability and weather seasons. So in terms of resource quality, offshore is also leading in terms of consistency. Variability, lowest variability due to stable offshore wind patterns. Onshore has medium variability. The solar PV is quite dynamic, highest variability. Predictability is quite high because the variation is less, so naturally the prediction could be much easier in the case of offshore wind. Onshore is medium and solar PV is somewhere in between low to medium. Land requirement, obviously there is no land available on the offshore, so no land required. So in onshore we need a large land area, and solar PV very large land area required. And in terms of energy density, highest energy output per unit capacity that we can expect from offshore, medium and lowest in the case of onshore and solar PV respectively. And impact on grid, so we are going to have more stable generation, easier forecasting. Onshore is medium and solar PV needs storage or advanced grid support. Best use case is for large scale reliable power for coastal regions. Onshore wind is land-based wind corridors, and solar PV distributed or utility scale solar in sunny regions. So it's a lot of advantages also that we have listed there. So with respect to the tariff, offshore wind, the price per unit is 6 to 6.5 rupees, and onshore is 2.8 to 3.4. Solar PV is 2.5 to 2.9. And wind solar hybrid comes out to be around 3.1 to 3.7. So let's move on to the policy and regulatory frameworks for rapid growth of offshore wind energy. So policy recommendations include enact clear deployment mandates and roadmaps. So where we can legislate offshore wind targets with milestones for both auction volumes and permitting timelines, giving the industry long-term visibility on pipeline size and schedule. Establish single window or lead agency systems where we can focus on centralized all permit reviews under one authority to establish maximum review durations and reduce interagency. Embed overriding public interest in national law. Designate permit-ready zones in advance. Facilitate early stakeholder engagement. So So this is the overview of offshore grid delivery models, where we can see these are the steps involved in the overall execution. So first we need to evaluate the conditions at the site. Spatial planning will be also done, and we need to also study the environmental aspects as well. Then tendering, financing and procurement, construction and operation and maintenance, right? So the figure illustrates how responsibilities for offshore green delivery are distributed across different phases of deployment. This enforces, this reinforces how delivery models influence the pace, coordination, and efficiency of offshore wind expansion. So, further, I would like to walk you through the typical technology involved in terms of power conversion, and we'll also discuss about some of the research challenges and the ongoing research activities that we are doing at IIT Kanpur with respect to the wind plants. So we know the basic theory that how wind blows, and then based on the aerodynamic principle, the turbine starts rotating. And then because you might have observed that wind blades rotates very slowly. So, but the grid is at, let's say, 50 hertz or 60 hertz. So you need to have mechanical conversion also. So the gearbox is used from high torque, low speed wind turbines being connected to the grid. So we need low torque and high speed gearbox conversion. And then this is coupled to the rotor of the generator, and then stator is connected to the grid. So we may use different types of generators. I'll discuss especially the type 3 generator. Ultimately, you need polytronic switches and converters to actually synchronize with the grid, because the wind power is highly fluctuating. You may have to convert AC to DC and then from DC to AC. So you need inverters. Because we have inverters, then we need filters, and then the transformer to meet out the voltage levels as per the power grid requirement. So overall, there are three stages. Kinetic energy is applied to the turbine to convert it into mechanical energy, and mechanical energy is further utilized, transformed into electrical energy via the medium of magnetic domain. So, so there are various types of generators available. Type 1 is squirrel cage induction generator. It's more or less like fixed speed. So there is no reactive power support also being provided by the synchronous by these machines, induction machines. Rather, the reactive power support has to be rendered from the grid, or if you have some capacitor banks or statcoms that you can manage by yourself. And type 2 is called as wound rotor, where we use the wound rotor induction generator. There is some variation possible with respect to the wind speed harness, so up to 10%. However, there is no much reactive power support also can be expected from these generators. The most popular one, which is widely adopted across the globe, is type 3 generator, the famously called as double-fed induction generator. The name itself suggests that the generation takes place from both the sides, stator and the rotor. So a sweet spot of rotor speed variation is around 30 plus or minus 30%, because most of the turbines or the site conditions, the wind speed varies in this range, plus or minus 30%. So the converter's size required would be much cheaper as compared to the type 4. So make it more economical solution, and MPPT mode of operation, reactive power support, all of them is quite possible in this type 3 generators. So type 4, where we go for permanent magnet synchronous machines. So the complete wind speed variation is allowed here. But however, you may need full rated converters to convert from AC to DC and DC to AC. One good advantage with type 4 generator is if there is any dynamics that is seen on the grid side, that is not reflected on the machine side. Whereas in the case of type 3 generator, if there is a fault on the grid side, so that is reflected on the stator side. So that may lead to some research challenges, which I'm going to discuss in due course of presentation. So these are some of the schematic of the different types of generators. So type 1, type 2, type 3, and type 4. You can see here this is a double-fed induction machine where we have the rotor connected to the stator, the point of common coupling via these back-to-back converters, which can render various support. So this is a schematic of double-fed induction generator. I'll not go in detail of technical explanation about how it operates, but in simple terms, during the subsynchronous mode of operation, synchronous speed is, let's say, 1000 RPM. And at 1000 RPM, if the machine can generate electricity at 50 Hertz, I'm speaking from the Indian context because Indian grid frequency is 50 Hertz. So then if the speed is little less, maybe during the daytime, if speed is less, then the frequency will not be up to 50 Hertz. So what happens is from the point of common coupling, some power is taken with the support from grid side converter that is transferred to the DC link, and with the support from rotor side converter, whatever is the balance power required to make it 50 Hertz is taken from this rotor side converter. And from the grid perspective, it looks like as if 50 Hertz power is injected from the machine. In the case of super synchronous mode of operation, the wind speed increases, so there is excess of power beyond 50 Hertz. So that is drawn out from this rotor side, and 50 Hertz component directly flows through the grid, and through the rotor side converter, grid side converter, this additional component of power is fed to the point of common coupling, so making it more steady throughout the operation of various wind speeds. So the main objective of rotor side converter is to extract maximum power from this machine, whether it could be subsynchronous or super synchronous mode of operation, and also to make it operate at unity power factor as far as possible. And the grid side converter is supposed to maintain this DC link voltage constant, and also it can render reactive power support as well. So these are the control schemes for the various converters. So this is the hardware prototype that we have developed to study the impact of wind energy conversion system on the grid and the dynamics of grid and the solution that we can offer from the wind energy conversion side. So that can also be studied through this kind of hardware prototype. So both bidirectional study is there, impact of renewable on the grid and impact of grid on the renewables. So we have RTDS simulator, and then which can help us to simulate the power system network. And then we have a programmable grid voltage source. So RTDS is connected to this programmable voltage source. And then to this grid, we can connect our hardware prototype. You can see here the converters, and this is the FPGA controller that we have used. And then this is the machine, double-fed induction, the motor generator unit. So we use DC machine to emulate the characteristics of the actual wind turbine, and it is connected to the slip ring induction machine. This DC machine is connected to a controlled through the DC to DC converter. So we can emulate the characteristics of actual wind turbine by changing the duty ratio of the switching pulses that is given to this DC to DC converter. So overall, we can actually bring the actual turbine generator combination to our lab and see how the dynamics are studied basically. So just some of the results to show you how is the startup and synchronization process that takes place. For the step number 1 is the acceleration of the rotor, then the activation of the grid side converter so that you can maintain the DC link voltage constant. Once you have the DC link voltage constant, why do we need to accelerate the rotor? First of all, because the converters are low rated. So we are actually generating the voltage from the stator side by giving voltage from the rotor side. So if you have a good amount of speed at the rotor, so we can because it's connected through slip, so even with the smaller voltage at the rotor side, we can build up the voltage at the stator side that can be connected and synchronized with the grid. So first we accelerate the rotor and then activate the grid side converter, maintain the DC link voltage constant, and then activate the rotor side converter, generate the voltage which is necessary to be synchronized with the grid, and then synchronize with the grid by checking the phase angle, voltage, and frequency. And once you have synchronized, then you start feeding power to the grid. So you can see this is a synchronization process. Eventually the voltage builds up, and then once the voltage is closely within the range of grid voltage, so you can synchronize and then starts feeding the power. So these are the different currents, three-phase DFIG currents, active power and reactive power for the three-phase. So maybe I'll just discuss one of the research work. In fact, this I have done during my PhD. I'll not take more than 5 minutes. So one of the research challenges which is predominantly studied by various researchers across the globe with respect to this type 3 wind energy conversion system is the fault rate through. So if there is a fault on the stator side, maybe a remote fault on the grid, so what happens is the grid voltage collapses. The flux, which being the state variable, does not allow sudden transition basically. So, but the stator, but the rotor is rotating because mechanical inertia is there. So, but the stator flux dips. So there is a constant flux now seen from the rotor side. Henceforth, a huge amount of voltage or magnetization is being induced on the rotor side, and then the voltage is induced on the rotor as well. So, but the converters are not rated up to that capacity. So that will damage the converters, switches, DC link capacitor. Overall, the system becomes quite unstable. This what we call it as fault rate through. So especially in this work, we have considered a specific case scenario where the fault is assumed to take place before the fault current limiter. So various hardware and software solutions have been reported in the literature where the researchers indicate that having fault current limiter after DFIG may address the solution to certain extent. But due to some reasons, if this fault current limiter is situated far away from this DFIG to have a better protection coordination, then there could be a chance where the fault can happen before fault current limiter, in between fault current limiter and DFIG basically. So instead of supporting the system, the fault current, the very presence of fault current limiter may deteriorate the condition. So we have considered this case scenario, and we have come up with the novel control switch configuration and to offer the solution so that we can improve the fault rate to performance of the type 3 wind energy conversion system. So these are some of the results you can see here. Once there is a voltage dip, there is a shoot up in the current and the voltage as well. So this is the topology that we have proposed. There are 4 switches which are formulated, and they switch accordingly so that even if fault happens before fault current limiter, from the DFIG perspective, it feels like as if the fault has taken off the fault current limiter so that we can improve the fault rate through. So these are some of the hardware results. So I will not go in detail, just to indicate that we are working rigorously in this area as well. So with this, I come to the conclusion of this presentation, that overall we have discussed about the various aspects like market and the potential of the offshore wind capacity, the challenges and the advantages of offshore, the tariff comparisons, and some of the research studies also being carried out. So with this, I'll conclude my presentation. Thank you so much. And I now request the host to take up the session. Yeah. Thank you.
Thank you, Dr. very much for your comprehensive presentation on highlighting on the potentials of offshore wind that is mainly available among the SAARC countries. And presently, we are focused more on harnessing solar power and onshore wind. But ultimately, there will be a time when we have to get up for harnessing the potential available from the offshore wind capacity. So maybe I think this will be just starting for, especially for the SAARC members, member countries. So someday it will be helpful in at least formalizing our strategies in and knowing or sharing knowledge of what the difficulties we are facing in the harnessing of or the advantage we are having while harnessing offshore wind. And with this, I would like to, the floor is open for, will open for the question and answer session. So if anyone has anything, please raise your hand or firstly, please introduce yourself and uh, please ask the questions so that our expert will facilitate to answer.
I can see Asan Javed ji has raised his hand.
Thank you very much, Mr. Tandon, for allowing me the opportunity to ask this question. So, Dr. Guru Raj, it was an excellent presentation. I really liked the technology aspects which you had mentioned in your presentation. So, my question is regarding more on the policy side. Like, for example, we see that in South Asia region, there is excess land available and there is a lot of onshore wind resource potential in most of the South Asian countries. And they have been developing these onshore wind turbine technologies for a long time. Like, for example, India and Pakistan have experienced lots of wind turbines in their country, and they've been implementing more in coming times. So now we come up to this new technology, which is offshore, which is definitely expensive in its capital cost, but plus on top of that, the O&M cost, as far as I know, is very high for the offshore comparable to the onshore technology. But definitely it has some advantages like high energy output. So in your opinion, what is the cost benefit analysis for these two technologies if we see on the comparison of offshore and onshore? And like I mentioned about some of the advantages of onshore, and then this, why would the member state delegates or policy makers would stop the onshore technology and go for this offshore? Do you have some benefits in your mind which you can offer to the participant and us? Thank you.
Yeah, maybe a very nice question. I mean, thanks for bringing out this. What I strongly feel is maybe at some point of time, land could be the crucial thing. You may say that, we may have sufficient land to expand, but ultimately there is a bottleneck with respect to the land. Eventually, we will like we may have to look out the spaces apart from what we can have at onshore, because lot of energy demand is going to increase because of data centers and growing energy requirement across the world. So we may have to look into this offshore. The land could be one such motivation to go for offshore. And then apart from that, let's say if the technology goes to certain level where we say that already there is a prediction that offshore wind turbines have better capability of extracting energy because of stable wind profile. So to make it more stable, make it more resilient, because that is the most challenging thing that we have to look into, because as we are going forward for more dynamic renewables, wind and solar. So currently this grid is very, very stable because it is most of the generation is taken are produced by this coal-fired power plants. Synchronous machines, they are quite stable, and inertia is also there. But as we remove these synchronous machines from the picture and we move forward for more renewables, so naturally we need to look forward for those renewables which can give more stable operations. So I strongly feel offshore can offer that kind of solution. in terms of bringing stability, adding more stability to the system. So that could be another technological edge that we can get from the offshore plant.
Doctor, thank you very much. So, is there any other questions from the participants? You could please.
Sanjay again.
I'll take this opportunity again to ask Dr. Gururaj about one aspect. So very briefly, I would like to know, Mr. Gururaj, that we know that India has implemented the offshore wind policy back maybe 7-8 years ago. I don't remember the exact date when they implemented the offshore wind technology policy. So what have been the core barriers or challenges being faced by the member state India in developing these offshore technology? I would like to know so that other member states could also learn the current barriers which are not helping to implement this offshore in India.
Yeah, if I remember, they have, in fact, they started this offshore plant and then it was functional and they could not maintain basically, and it was stopped as per my knowledge is concerned. I think the barrier could be that the operation and maintenance, I guess. So there was some challenges over there. And then, of course, cost could be installation cost is quite expensive. So we need to work on this to make it more feasible.
Thank you very much.
Thank you.
Can you, may I ask Dr. Atik to go ahead with the question, please? So,
I'm not able to hear.
yes. Can you hear us now? Hello, doctor. Doctor,
He is muted himself. Dr. Atik, can you please unmute yourself, please?
Dr. Atikur Rahmanji, kindly unmute yourself.
Okay, thank you, Gururaj, for sharing wonderful information regarding the offshore wind technology. My question is that, is there any operational or pilot projects globally that integrate floating offshore wind projects with solar PV in a hybrid configuration?
Oh, nice question. As per my knowledge, there is no such pilot as of now. Maybe at some capacity it may be there, but to my notice, I don't have such information.
Thank you. Thank you so much.
Thank you.
is there any more?
Thank
So, if there's no more further questions, we will conclude this webinar. Doctor, thank you very much, and thank you very much, and the participants. We look forward to such events in the future also. So, thank you very much.
Thank you so much. Namaskar.